Welcome to the Explainer. We throw around the word information all the time, but what does it really mean, especially when scientists talk about it? Today, we're going to break that down.
All right, let's just jump right into the deep end with a question you've probably heard a bunch. Is reality just made of bits? Are we all living in some giant computer simulation? Is everything around us, everything, just a long string of ones and zeros?
Well, the source material we're digging into today says not so fast. It makes a pretty bold claim right from the get-go. Information is super useful for sure, but it's not the actual stuff reality is made of. And we're about to find out exactly why. Okay, so to really get this, we've got to wrap our heads around a really key difference. It's the difference between describing something and explaining it. They might sound like the same thing, but trust me, they're not even in the same ballpark.
And this really nails it. A description, that's your blueprint. It answers what is it. It shows you the layout, the shape, how it acts. But the explanation, that's the engine. That's the part that answers why. It shows you the actual machinery that makes it all work. And here's the kicker. Information theory is an amazing blueprint, it really is, but it doesn't give us the engine.
So, this leads to three big problems if you try to build reality out of information. First, there's no engine, right? Bits by themselves don't do anything. They don't interact. Second, you always need someone or something like a computer on the outside to look at the bits and say what they mean. And that brings us to the third point. It all means information is great at describing things, but it has zero power to explain them. I love this analogy. Think of it like a team. Math is the writer. It gives us the language to describe the universe. Physics is the engineer. It explains the how and why things actually work. And philosophy, that's the guide that helps us understand the bigger picture, what it all means. Information theory, the star of our show today, is 100% on team math. It's a powerful language for describing stuff. Okay, so if information is all about describing things, how do you actually measure it? Let's stop talking in abstracts and get real. We're going to use a super simple example, just rolling a normal six-sided die. The real question here is all about efficiency. What's the fewest number of symbols you need to send a message to your friend that says, "Hey, I rolled a 4"? And believe it or not, the answer isn't as obvious as you might think. Let's think it through. You could just use the number 4, right? But our number system has 10 symbols, 0 through 9, and we only need 6 for a die, so that's kind of wasteful. What about binary, the language of computers? Well, 2 bits only gives you 4 combinations. Not enough. 3 bits gives you 8 combinations, which is too many. So the perfect, most efficient number of symbols has got to be somewhere in between 2 and 3.
So, how in the world do you find a number that's between 2 and 3 symbols? This is where math comes to the rescue. There's a brilliant tool that's basically made for this exact problem. It's called the logarithm.
So, for our problem, a die with 6 sides, in a binary, base 2 system, the calculation is simple. You just take the log base 2 of 6.
And what do you get? Boom, 2.585 bits. And that's the whole point. It takes exactly that much information to communicate one of 6 possible outcomes. The fact that it's not a whole number might seem weird, but that's what makes it so precise. It's a pure mathematical quantity.
All right, that's pretty cool, but all of that worked because we assumed we had a fair die where every side had an equal chance of landing. But what happens when we start to cheat a little? What happens if the die is loaded?
So how does that change things? If we load the die, making some results super common and others really rare, does that actually change how much information you get from a roll? What do you think?
Okay, let's picture a seriously crooked die. It's weighted so that rolling a 6 is almost a sure thing, like a 90% chance. Landing a 2, 3, 4, or 5 is a super long shot. And rolling a 1? Forget about it. It can't happen. Now think about it. If I roll this crooked die and tell you, "Hey, I got a 6, you'd just be like, "Yeah, so what? It's expected. It's boring." But if I told you I rolled a 4, whoa, now that's a surprise. That feels like you just got a big piece of news, a lot more information, right?
And that feeling, that sense of surprise, is exactly what the legendary Claude Shannon, the father of information theory, captured in his work. His big idea was that information is literally a measure of surprise. The formula looks simple, but it's genius. It basically says the less likely an event is, the more information it contains. Simple as that.
So let's run the numbers. The chance of rolling that 4 was just 1 in 40. You plug that into Shannon's formula and you get about 5.32 bits. Now get this, that's more than double the information you get from any single roll of a fair die. That's the surprise factor, turned into a hard number.
Okay, so this link between probability and surprise is cool, but it's not just some clever math trick. This is where it gets really mind-blowing. This exact same idea, this same mathematical structure, shows up in one of the most fundamental areas of physics.
Just look at Boltzmann's famous formula for entropy. You know, the thing that measures disorder in a system. It's the same structure. You've got a logarithm that's counting something, in this case W, which is just the number of ways the atoms and molecules in a system can be arranged. At their core, both information and entropy are about the same thing, counting possibilities.
So what does this all mean? It means information isn't some physical thing that exists out there in the universe. It's a property of what we know about the universe. It's a tool, a framework we use to measure things, based on how we decide to count their possible states. It's about our knowledge, not about the thing itself.
And that brings us right back to where we started. Yeah, you can describe pretty much anything you want with bits. You can describe a star, a tree, a person. But just because you can describe it with bits doesn't mean it's made of bits. Bits are the letters in the book, not the engine that wrote the story.
So here's the bottom line. Information is an absolutely essential tool. It's a language, a powerful one, that lets us describe our world with incredible precision. It lets us measure what we know and what we don't know. But we have to remember the golden rule. Don't confuse the map with the territory. Information is the map.
And that leaves us with one last really big question to chew on. If math and information give us the blueprint, the what, then what gives us the engine? What is the machinery that actually provides the explanation, the thing that answers the biggest question of all? Why?